Should be better now. So you have two major portions of the calculus. So you've got your derivative calculus, the integral calculus. We will introduce the derivative in this chapter, and the integral calculus will really come in the last two chapters that we cover. So it's really about the last two chapters. So basically the last test, weeks 5 and 6, are all going to be about the integral. So what you want to understand is the definition for the derivative and the integral, the two main parts of calculus, are based on this thing called the limit. So the very definition of these objects we're going to be developing have the limit in the definition, which means in order to understand anything in this course, you really have to understand the limit and understand how that works. And for the good news is once we wrap our brains around the limit and we kind of get how this works, it's going to be pretty straightforward in how we usually apply the limit. We will occasionally have to do some extra work, but it just seems really weird at first, this idea of a limit. So it definitely takes some practice to get good at. And then once it clicks, you kind of go, oh, why did I think that was so complicated? It's actually not too bad. And then that's going to set the stage for us to get into the derivative, which we'll be doing by section 2.4. We'll get into the derivative, and then we spend like what, 2.5 chapters talking about the derivative, developing more tools with the derivative. And the limit, you can't really have a derivative without a limit, but the limit is also going to make appearances as well along the way. So this really important idea of the limit, don't take it lightly. You want to make sure that you're good with the limit so you can understand how these things go. So we're going to develop kind of an intuitive definition of what the limit is, and then try to apply it in a few different places. So we're going to have typical limits, which we can think of as a two-sided limit. We're going to develop one-sided limits. We're going to have limits that can go to infinity, and then we're going to have infinite limits. And those last two people confuse because they sound almost identical, right? If I say infinite limits or limits at infinity, if you're not listening really closely, you can get confused about which one I'm talking about. So we're going to cover all that kind of stuff so that you'll be a little bit more comfortable with it. So fundamentally, when we talk about a limit, what we're talking about is we're really asking the question, what is the y value when the x value approaches a certain value? So like, for instance, let's take a look at this graph that I've got right here. So the red graph is actually the function that we're interested in. So what are these purple lines that I've got right here? Well, that's just the x value and the y value for a specific point. So it's that you can see where the x values and y values are going. So let's say that I take a point right around in here and I change where that point is located. So let's take like, let's go over here. Yeah, there's where I wanted it. So let's say that our x values are approaching 4. So I'm kind of going back and forth. Oh, actually, that would be, sorry, -1. So our x values are right around -1. So say we're coming from this side. When we talk about limits, what we're really asking is, what are the y values doing when my x values are approaching a certain number? So as my x values are approaching -1, my y values are coming up and approaching +1, right? See how that's working right there? My x values kind of coming in right from this side right here, and the y values are coming up here. So this line is representing the y values, this one the x values. So when we're dealing with continuous functions or continuous parts of functions, then limits are really straightforward. Like you might be looking at this going right now going, what's the big deal about an x value and a y value approaching certain things? Well, it's because we're going to jump into functions where this gets more complicated, and then you'll see, oh, that's why we have this more complicated tool. But fundamentally, that's what we're asking about. And if we jump over to the actual notation that excuse me, I'm choking there a little bit. Oops, that's not what I want. If I grab this. So this is what our limits are going to look like algebraically, right? So let's try to break down what these pieces look like. So the LIM, that's just our notation for limit. So whenever you see LIM, you automatically know, oh, we're talking about a limit in this circumstance. Okay, and before it, this diagram kind of makes sense once you understand what's going on. This is telling us where our x values are going. So this says we're concerned about x values as they approach 1. So that's an x value of 1. So you can always remember, oh, this is an x value down here. This piece is an x value. And we want to know what's happening as our x values are right around 1. Okay, this piece up here, this is our function. So this is the function, right? This is not the one we were looking at in a graph. This is a different one. This is our function, right? So you might have this written as y equals this, or you might have it written as f of x equals this, but this is the rule for the function that we're interested in. And then what's this piece over here? This is the y value. So this piece on the end is the y value. So remember I was saying that the limit is always asking what's the y value when your x values are doing a particular thing? Well, up front, they're saying this is what we're worried about. We're worried about the limit when our x values are going to 1. And then on the back end, it's saying, yeah, and the y values are going to 3. That's what's going on here. So you really want to make sure you break down this formula and understand all those individual pieces, and then you'll be surprised how much clearer it is when you're given a limit and you have to sort of dissect it and you automatically know, oh, there's my x value, here's my function, and then usually you're going to be figuring out this piece over here. Usually you won't be given this. This is what you have to figure out. This is what you have to calculate and come up with, okay? You'll also see this written in the following form. Right, you might just see that where we have the function notation written in there for some f of x. This may be because it may be very difficult to put your function in there. So you may only have your function as a graph. You might not have a nice clean rule like this. Like when we can put things in a nice easy function notation, it's really helpful, really convenient to do. But sometimes you can't. Maybe your function is just written in the form of a table, a bunch of x values and y values to go with them. Or maybe it's just a graph that doesn't have any other information. Then you can just call the function, and this would say, okay, we want the limit as x goes to 1 of whatever function it is that we've named f of x. And then we know we're concerned about the y values over here. Okay, so with that in mind, let's go back and look at our graphs that we were just looking at. So if we go over here, let's leave this other graph behind, and we'll now go to something like this. So let me change this to red. And I'll move it over. Oops. Okay, so now we have a little bit more of a complicated function here. Yeah, we'll leave it as y equals x. Actually, let's just clean things up a little bit here. So let's just say that these blue graphs are actually one function. Okay, so together they make one function. Well, we have a little bit of an issue here. So remember I said when we're dealing with continuous parts of the graph that limits are generally very straightforward. That's true. Notice what we have here to complicate things is a discontinuity. We have this break right here. This is what we call a jump discontinuity. To get from here to here, you'd have to make a jump, right? So sometimes you'll hear that term jump discontinuity. Well, we have a little bit of an issue here. So this is what, an x value of 2 right here. And notice that before we were asking what is the y value as our x values are doing a particular thing. So let's say our x's are coming along this x-axis and they're approaching 2 from the left side. Well, if I approach an x value of 2 from the left here, my y values are going up towards 2, right? So we would say that as x goes to 2, my y values are going to 2. Except we have an issue here. What happens if I approach 2 from the other side, where my values are coming from the positive side of things? Well, now as my x values are going to 2 from above, from the positive side of things, my y values are now coming down and approaching 4. Okay, so on this side, if we come from the left to x equals 2, then my y values are going up to 2. But if I approach from this side, my y values are coming down and approaching 4. So in this case, we would say that the limit doesn't exist because it depends how we approach 2, right? We're asking the question, what do my y values do when my x values are approaching 2? And the answer is, well, it depends. If your values are approaching 2 from the negative side, then your y values are going to 2. If your x values are approaching 2 from the positive side of things, then your y values are approaching 4. We get 2 different answers to that question, so we would say that the limit does not exist. Whenever we use the term limit and just say limit, like just the word limit, it's always understood that it's meant to be a two-sided limit, okay? Because that's the formal definition of a limit. We'll talk about one-sided limits in just a second, but right now we would say that the limit at x equals 2 of this function does not exist. Okay, so if we jump back over to here, we could change this up to look like 2. Let me come over here and grab this. The limit as x goes to 2 of our function. And you'll see people write this different ways. Some people will just write out does not exist, and it'll have that in the homework. Sometimes people abbreviate it with DNE for does not exist. But for our problem that we just looked at, we would say that limit as x goes to 2 of the function we were looking at does not exist because those, you can't answer the question, well, where are y values going? Well, it depends. They might be going to 2, they might be going to 4. It depends on your path to get there. Okay. So then this brings up the idea of one-sided limits. So remember, whenever we say limit, it's understood we mean two-sided limit. Otherwise, we can specify a one-sided limit if we want to. And the one-sided limit will capture that behavior we were just talking about. So notice if I just say, well, what's the one-sided limit as we approach from the negative side of things? Well, as we approach from the negative side of things, we said that as x goes to 2, our y values are coming up to 2. And as we approach from the positive side of things, right, as our x's approach 2, our y values are coming down to 4. So the way we would write this is that for a one-sided limit, what we do, remember that part of the function where, or the part of the limit that specifies what our x's are doing? We put a little bit of a notation on that. And I would put, so you'll watch right here, I'll make this a negative. And this now would become 2. And we'll copy that again. Make this a plus. And write that as a 4. Okay, so what does this mean? There's a slight bit of notation here. It looks almost identical, but different. See how there is this minus sign right here? That's indicating that we're talking about a one-sided limit in which x is approaching 2 from the negative side of things. Okay, so some people will call this a left-handed limit. It's fine to call it that. I usually like to think in terms of positive and negative because then I always know, you know, and then you can keep straight what direction you're coming from, but it's normal terminology to say left hand or right hand limit. So the limit as x goes to 2 from below of that function we were just looking at is 2. Okay, because the y values are, as the x values approach 2 from below, sometimes people say from below to mean from the negative side, and they say above to mean from the positive side. That's vocabulary you'll hear as well. So as our x values approach 2 from the negative side, our y values are approaching 2. And then look down here, we have this plus. That means the one-handed limit from the positive side of things. So we've got the limit as x goes to 2 from the positive side of things. Those y values were approaching 4. So see how the limit is always equal to some y value, like a specific numerical y value. Okay? So in this case, we would say the two one-sided limits exist, but they disagree with each other. Okay, one of the requirements for your limit, the full two-sided limit to exist, is that both of your one-sided limits have to exist and they have to agree with each other. So this is a situation where both of our one-sided limits exist, but see how they don't agree? One side says 2 and the other side says 4. That leads us to conclude that our full limit does not exist. Okay, if we did a problem where we got 2 for both of these, then the full limit would be equal to 2 as well. Okay, so your two one-sided limits both have to exist, and they have to agree with each other. That's a requirement for things. Okay, let's go back over here. And I'm not seeing any questions. Okay. So that's one thing we want. Oh, okay. So let's go back to this. So then you might get into questions where you ask, well, what would happen if I was trying to figure out a limit over here is easy, right? Because again, parts of your function where you're continuous, limits are really easy to calculate. You basically just calculate the function value. So things like a polynomial where you're continuous everywhere, really easy to calculate limits. You just take the function value, right? But what about when we get over to something here where we have, like, say, a vertical asymptote? So let me clean some of this up here. So if we look at, say, what is that, x equals 1? Right there. So we've got a vertical asymptote right at x equals 1. So what would the limit be here? How would we go through and describe that limit? And now we start to get into some sort of nuances, some subtle details that we have to keep straight. It's really easy to get confused when we get down into these details, but we want to keep this part straight. So we wouldn't have an overall limit because we can see, well, what about my x values as I approach from above, from the positive side? It looks like they're shooting down towards negative infinity. And then over on this side, as I approach x equals 1 from the negative side, my values are shooting up towards positive infinity. Now, I said a minute ago that for a limit to exist, it has to be equal to a specific number, and that's true, but then we go through and we make it a little bit confusing with the notation. So let's take a look at that notation again to describe this picture right here. So I can't show you both at the same time. So try to kind of remember what this looks like. And now we'll jump over to that notation again. So for right here, and what were we doing? X was going to 1, was it 1? Yeah, x was going to 1. So let's look at as it goes to 1, 1, 1. Okay, so in this case, again, the limit itself is actually going to not exist for that. The limit will not exist for that function, but for a kind of the same reason, but slightly different than before. So remember, we were approaching the limit as x goes to 1 from a below, and that function was shooting up towards infinity. So what we would write here is the infinity. And we would do the same down here. Now, nope, there we go. So this might seem a little bit weird because I've been specifying that whatever we put over here has to be a specific number, and that's true for the limit to exist. But so technically what happens here is we would say, to be proper with our language, the one-sided limits don't exist, because for a limit to exist, you have to be approaching a specific number. So this limit doesn't exist, but we don't write does not exist. We write infinity right here. So that seems kind of weird. Wait, it doesn't exist, but I'm still labeling it with a symbol? And the answer is that we're describing the way in which it doesn't exist. There are many different ways in which a limit can fail to exist. And by writing infinity here, it's basically giving us a clue. Oh, it looks like there's a vertical asymptote right there. So rather than having to do a bunch of more work and figure out that there's a vertical asymptote, this is basically cluing us into, oh, there's a vertical asymptote. Oh, and this one should have been negative infinity, right? That one's supposed to be negative infinity down there, the second one. So the top one's going to infinity, the bottom one's going to negative infinity. Technically, we say that neither one of these one-sided limits exists, but we still write it so that we remember, like, oh yeah, that's where that vertical asymptote is occurring. And sure enough, we can see, if we're right here, we can see that vertical asymptote is occurring right where we said. Okay. Now, notice for these two one-sided limits that the values disagree. Well, what if we did one where they agree? Let's see. So that should be right there. There we go. So think about this function right here. In this case, If we look at the limit from the negative side of things, it's shooting down to negative infinity. And here, if we come from the positive side of things, it's shooting down to negative infinity. So in this case, at least the two one-sided limits agree. The problem we did a minute ago, our two one-sided limits disagreed because one was infinity and one was negative infinity. But in this case, they are both negative infinity. So in this case, since they agree, we would write, instead of writing does not exist for the limit, and technically it doesn't exist, but we give ourselves a better clue by writing that it's negative infinity. Negative infinity. So when they agree, we still write negative infinity. And I know it's weird, and it definitely confuses students where you're saying, wait, you're telling me the limit doesn't exist, but I'm saying it's equal to negative infinity, right? Because the limit has to be equal to a specific finite number. This is just a way of saying, hey, we've got a vertical asymptote there, and the values are going to negative infinity. So it takes a little getting used to, but should be good when once you practice a few of those. Okay. All right, let me catch my place here. All right, so let's talk about, so these are what we call infinite limits, right? Where you're getting either infinity or negative infinity for your answer. Those are called infinite limits, right? That's slightly different than what we're about to look at, which is called limits at infinity, right? That's different. Let's simplify this. So when we talk about limits at infinity, essentially what we're talking about is end behavior. So remember, in your college algebra class, pre-calculus class, whatever you took, you spent some time talking about end behavior, mainly end behavior of polynomials and end behavior of rational functions. So that end behavior, it's basically going to translate over perfectly to what we're doing, except in calculus, we use this new language of limits. So we talk about the limit at infinity. So if you think about it, the limit at infinity, well, infinity is basically like, for example, here we're going down this x-axis forever. You just keep going down it, and you don't stop. There's nothing bounding you, keeping you from moving ahead. You're just going down it forever. There's not a point on the number line where you reach infinity. Infinity is not a number. It's more like a verb. It's an action saying we're going down the x-axis this direction. So when we talk about the limits as x goes to infinity, we're really just asking the question, what's the end behavior of this function overall? So for this, we can see the end behavior is that it comes down and it's approaching 0, right? So the way we would write this we would now write this as, let's mute that one and that one. What's going on? Oh, there we go. Okay, I wasn't scrolled up far enough. Okay, so if we just look at the top one for a second, let's ignore this other one for just a moment. Notice how the notation has changed a little bit. So it's now written as the limit as x goes to infinity. So this is a limit at infinity because we're talking about the x value going to infinity. We're really wondering about the end behavior on the right side of the graph. So for that particular function, we saw that as I go down the x-axis, my function values are squeezing down towards that x-axis. In other words, I'm getting 0 for my y values. We never actually get 0 in the function 1 over x, but we get infinitely close to 0, right? Think about just taking numbers and putting zeros on the end. So you've got 1, 10, 100, 1,000. Each time you plug one of those values into our function, that fraction is going to get a little bit smaller. It's getting closer and closer to 0, but it never quite reaches that point. It never quite gets there, okay? So this is what we mean when we say limits at infinity. And we could ask the other question, well, what about on the left side, right? What if I wanted to go towards negative infinity? Well, we can ask that same question. What is the limit as x goes to negative infinity of our function? And if we jump back over to that graph, we can see that it's doing the same thing, right? It's coming up and it's going towards, it's going towards 0 as well. They're coming from below. So in this case, your numbers will always be just slightly negative, but they'll be getting closer and closer to 0. So in this case, we would still say the limit as x goes to negative infinity, as x is going to negative infinity, our y values are getting closer and closer to 0. So that's the way you state that question of what are the y values doing when our x values are doing a certain thing? Well, when the x values are going to negative infinity, the y values are going to 0. Okay, that's how we state that. Now, we have to remember some rules about how this works. And like I say, the good news is we're basically just wrapping up what we learned as end behavior in the previous course. We're wrapping it up, putting a new name on it, using some new terminology, and calling that limits at infinity. So on page 113 in section 2.2, there's a little blue box that reviews end behavior. So if you've kind of forgotten that a little bit, this will remind you how that works. So let's spend a few minutes looking that over. Kind of remind ourselves because it's going to be pretty important. So if you can kind of remember how this works now, it'll be very, very helpful for you going forward. So let's say we've got a situation like the following. Okay, so say we wanted to know about the end behavior of this. Well, if you look on page 113 in the book, they give you the 3 cases. So what you're always going to look for when you want the end behavior of these rational functions, you're looking at the degree of the polynomial in your numerator and the degree of the polynomial in your denominator. Okay, so this is how it works for rational functions. And you're comparing those degrees. So notice in this case, we have the situation where the degree of our denominator is bigger than the degree of our numerator. Okay, that's the situation where you can always think about this in terms of what does a fraction do if I have, say, a little numerator and a big denominator? Or what if I have a big numerator and a little denominator, and think about what that would do to your fraction. So if you notice our function right here, this denominator, when I start plugging in really, really big values, right? Remember, we're sending x to infinity, so we're talking about massive numbers. You know, think of a number with 1 billion digits in it, right? If I take that and plug it into this function, I'm going to get a big number in the numerator and a big number in the denominator, but the denominator is going to be so much bigger than the numerator that it makes the numerator look like it barely exists, right? Because if I cube something with 1 billion digits, that's going to be way bigger than if I square something with 1 billion digits. So what's happening is my denominator is growing at the rate of a cubic, whereas my numerator is growing at the rate of a square. So that means that my denominator is going to outpace the numerator. So then we stop and think about fractions. Okay, what does a fraction do if I have a big denominator and a small numerator? What happens? Oh, that gives me a small fraction, like 1 over 100, right? Big denominator, small numerator. I get a really tiny number. And that's what we see happening in the graphs. We see these numbers shrinking down towards 0. So whenever the degree of your denominator is bigger than the degree of the numerator, then your horizontal asymptote is going to be y equals 0. It's going to be the x-axis. So that's what would lead us to believe in this case, okay, so my limit as x goes to infinity will be 0, because that's what my y values are approaching, is 0. Okay, and the same on the other side. If we zoom out, you can see they're coming up and leveling out right around 0 as well. Okay, so that's one of the 3 cases. The degree of the denominator being bigger than the degree of the numerator means your horizontal asymptote will be y equals 0, meaning that the limit as x goes to infinity or negative infinity will also be 0. Okay, it's like 3 different things. You got to just sort of associate all of those together so you can kind of follow along with them. Okay, so what's the other case? Well, what if we had the case where the degree of the, let's do this one. Let's say the degree of the numerator was equal to the degree of the denominator. Okay, so what happens here? So a couple things I want to point out. It looks like our horizontal asymptote is leveling out at y equals 2, and it is. But one reason I want to show this is sometimes we get kind of lazy and we'll say things like, well, a function can't cross its horizontal asymptote. Well, a function can, and we see it right here, a function can cross its horizontal asymptote in the middle of the graph. Where it can't cross a horizontal asymptote is towards the ends. In other words, see how this graph is coming up and it's getting closer and closer to the green line right here? It's never going to cross that green line. It's just always going to be getting infinitely closer to the green line, but it's never actually going to touch it. So when we say things like, well, the function can't cross a horizontal asymptote, horizontal asymptotes are really only important on the ends of the graph, the end behavior. So that's really where we're talking about that it can't touch, right? It's a minor point, but sometimes people get confused about that. So in this case, if the degree of the numerator is equal to the degree of the denominator, what you do is you take the ratio of the coefficients on those 2 highest terms. Because in this case, our numerator is growing up at the rate of a square, and the denominator is growing up at the rate of a square, right? So the only difference between these two is the fact that there's that 2 multiplying the term on top and nothing multiplying the one on bottom. So then, in fact, technically, you'd think of it as being 2 over 1, right? The ratio of those coefficients on the x squared terms would be 2 over 1. But then, of course, if we have to write 2 over 1, we just write it as 2. We don't write it as 2 over 1. Just 2, but that's where that's coming from. So if the degree of the numerator equals the degree of the denominator, we're looking at the ratio of our lead coefficients. We're basically applying that lead coefficient test that we learned in college algebra. We're applying it now in a calculus setting. Okay, so that's what's going on there. And then the last scenario is kind of the easiest one. If the degree of the numerator is higher than the degree of the denominator, that means your numerator is going to blow up faster than your denominator. So what happens when you have a fraction with a big numerator and a small denominator? Well, the whole value blows up, right? So if we put something on here that's higher degree, say we make that a 3, then you can see what's happening here. Our end behavior is that these, move it for you. Our end behavior is that the ends on this side, we're shooting up towards infinity. And on this end, we're shooting down towards negative infinity. So in this case, we wouldn't have a horizontal asymptote at all. You may recognize there actually is an oblique asymptote here or a slant asymptote. We learned those in college algebra. We're actually not going to deal with them too much in here because most of the time, if your stuff's going to infinity, that's all you care about is that it's going to infinity. The slant asymptote would describe how it's going to infinity, but if we just know our values are blowing up towards infinity, that's usually good enough. Same as over here. So the last case is that if the degree of the numerator is greater than the degree of the denominator, you have no horizontal asymptote, and your end behavior, the limit, is that those ends are either going to infinity or negative infinity, either one of those. Okay. Right. Let me see where I'm at here. Polynomials are great, right? I've mentioned a few times you're going to be glad whenever you have to deal with polynomials in this class. That's because as being smooth, continuous curves, they behave like really nicely. So if you notice, if we've got, say, some polynomial here. So we've got some polynomial. But being a normal polynomial, this is smooth and continuous, so there's no kind of weirdness going on. If you ever want to calculate the limit at a specific point somewhere on a continuous graph, all you have to do is find the function value. Because, let's blow this up here. If I'm asking you here, like where are these values going as my x, let's look at this. As x is approaching 2, what are my y values doing? Well, the y values are all well behaved because we have a continuous graph. So the limit from below is going to 0. The limit from above is going to 0. And then since both of those one-sided limits exist and they agree at the value of 0, then our limit is 0. So see, anywhere on a continuous function, to calculate the limit, all you have to do is just calculate the function value at that point, and that will be the limit. So like here, the limit as x goes to 0 is 0. The limit as x goes to 2 is 0, right? The limit as x goes to whatever this point is right here is, looks like -4, right? It's all very predictable and well behaved. And for like a rational function that we were looking at, they're pretty straightforward as well, because notice this graph is continuous most of the time. So any limits you wanted to calculate on this continuous part of the graph, really easy. All you have to do is calculate the function value at that point, and you have your limit. The difficulty arises when you have some type of discontinuity. So see, we have a discontinuity right here at x equals 0. Now all of a sudden we have to investigate more, and we have to say, well, the one-sided limit coming from the negative side is going to negative infinity. The one-sided limit coming from the positive side is positive infinity. You know, and then we have to start bringing in those tools to discuss that discontinuity in that way. Okay, so wherever you have a continuous part of your function, it's going to behave very nicely, which is good, right? That's very convenient. All right, let me see what I wanted to say here. We got a little time left. About that. Okay, so getting into 2.3 continuity. So the good news about continuity, there's sort of a strict definition, and then there's this intuitive definition that we use for continuity. And for most of what we do in this class, we're going to get away with kind of the loose definition, the intuitive way of thinking about it. But we do want to know and understand that strict definition for the polynomial. So let's say we've got, let's move this. Our loose definition for continuity is just that if you can draw your graph without lifting your pen off the paper, then it's continuous. So if you think about it like, here, I'll go back to our graph. You couldn't draw this without lifting your pen off the paper, right? You'd be able to draw you'd be drawing all along here, and then you'd get to this point, and then you would have to jump, you'd lift your pencil up, jump up to here, and then you could draw the rest of the graph. Well, that point at which you had to lift your pen up or pencil, that's where your discontinuity is occurring. So that's the easy way of thinking about continuity. Did I have to lift my pencil up in order to finish the drawing? Yes? Okay, then I had a discontinuity right there. That's where that's occurring. Now, that's not very mathematical or scientific thinking, but that's the concept of how we can think about it. The formal definition we actually already just used, which is convenient because it might help you understand it. So let's say that we have a limit where our x value is approaching a specific value. So in this case, like a. Then we know we're continuous if the limit is equal to the function value at a. Right? We just kind of use this the other way around, where this is the definition to prove continuity. But if you know you have continuity, then you can use this definition the other way around. That is, you can calculate your limits by looking at the function values, right? So this is kind of nice. We'll do this with calculus a lot, where we'll develop some kind of tool or definition, and we'll actually use it two different ways. We'll use it in two different directions in order to do things. So for instance, like to do an actual problem, this might look like, you know, the limit as x goes to 2 should equal f of 2. So for a continuous function, this would be true. The limit as x goes to 2 of our function would be the actual function value evaluated at 2. Right? So this is what makes it so easy for polynomials. If you want to know the limit of a polynomial at a specific point, just evaluate that polynomial at that x value, and then you're good to go. You've got your limit. Right? So for polynomials at a finite value, it's easy to calculate limits. For a rational function, as long as you're not trying to calculate the limit where there's like an a vertical asymptote, then you get to do the same thing. You just plug it in, calculate the function value, and that's super easy to do. So that's our basic takeaway of continuity. We'll deal with all sorts of discontinuities moving forward. We looked earlier at jump discontinuities. Sometimes you just have a hole poked in your function. That's a type of continuity. All these discontinuities can cause us extra work in calculus, right? Because as we've seen, where your function is continuous, it's very easy to calculate the limit. The difficulties come in when we have a discontinuity like here, or that jump discontinuity that we had earlier where there was a break between our two functions. You could have piecewise functions where your pieces in your piecewise function aren't anywhere near each other, right? You get all these discontinuities, and then we're going to have to start taking a closer look at things. We're going to have to start evaluating those a little bit more. And so they give you some, like on page 123, I guess it starts on page 122. They start giving you some nice properties, and this is basically what I've been talking about when we've been looking at it. Let's see, let's move this over. So they're kind of summarizing some of what I've talked about. So for continuity properties on page 122, it makes sense. One of them they give is for a constant function where k is continuous. A constant function is continuous everywhere. So remember when we say a constant function, that just means like y equals 3. They're just saying the y values are always 3. It's continuous, right? Think of this as being a bank account where you don't spend money and you don't deposit any money. It just stays the same all the time. You've got $500 in this account. It just stays $500. Your graph would be a constant function. Okay, so the limits for a constant function are easy because a constant function is continuous. Therefore, if you wanted to know what's the limit as x approaches 10, well, it's 3 because the y values are all 3. What's the limit as x approaches 5? 3. What about 6? 3. It's always going to be 3. You just look at this and you evaluate the function because it's continuous there. Same for any polynomial or rational function as long as you're away from the vertical asymptote. And then they get into like even and odd roots. We won't actually have to deal with that a ton. I highly encourage you when you're doing this section in fact, I would encourage this for the whole course. Like for me, if I sit down to work on calculus, I'm probably going to have Desmos open. So this website I've been using, DESMOS, Desmos, it's a really easy to use graphing utility. I would probably have it always open because one of the things I noticed when I've been answering questions from students in the last week is that sometimes it becomes clear to me, oh, this person would have caught their own mistake if they had graphed the function. So like in a normal situation on ground, if we were teaching on campus, we'd all have graphing calculators because it's really helpful to graph when you're in a classroom like that. But just using Desmos to get a quick graph, if you're ever stuck on a problem, pull it up on Desmos and look at it. Because, I was answering questions where people were like, well, I'm getting the wrong vertical asymptote. But what happened was they had their signs wrong when they were factoring. Well, if you graph it, you'll probably catch that because you'll go, wait, I thought the vertical asymptote should be at 3, but this graph is saying it's at -3. And then you'll catch the fact that you just got your signs wrong in the factoring and can fix it. So I would recommend basically every time you do a problem in this course that could any way involve a graph, you should graph it. You should put it on Desmos and see what the thing looks like. And that's a lot of what we're going to be doing in calculus anyways. We do a lot of back and forth between the algebra and the graph. So we'll do things algebraically, and then we'll use that to tell us things about the graph. And then we'll do some stuff graphically, and we'll use that to tell us stuff about the algebra. So I would encourage you to get comfortable with that Desmos. It's a huge help, right? It's definitely a huge benefit. And then I would encourage you, I'm going to put up a video on this probably tomorrow. I'll get it up, about constructing sine charts. So sine charts are hugely important in the calculus. So pretty quick here, we're going to start constructing sine charts, and you need to be able to do it correctly, because one of the things we're going to start doing when we introduce this thing called the derivative is we're going to start looking at derivatives and then making sine charts for those derivatives, and those sine charts are going to give us very exact, very detailed information about our original function. So we'll be able to make really powerful statements about our original function, but we're going to need sine charts in order to do that, right? In order to get that calculated. So you might start reviewing sine charts. I'll get a video up there tomorrow so you can remember how to do that, but don't take that lightly. It's not a thing we can just skip over. We're going to start developing problems by the end of, is it the end of chapter 3 where I think, it'll be chapter 4. By the time we get to the end of chapter 4, we're going to have problems where we have like 7 or 8 parts to the problem, where you're doing 7 or 8 different things. And some of those steps in the middle are going to be make a sine chart for this thing, right? So we use sine charts in college algebra. We use them to determine where a function was, say, increasing or decreasing. That's actually exactly what we're going to do, but we're going to be applying it to derivatives. So we want to make sure that skill is sharp. So anyways, take that part of the homework seriously, because it will come up quite a bit. Okay, we definitely don't want to start derivatives with only a few minutes left to our meeting, because derivatives, like I've said, are sort of half the calculus course is derivatives. So we're setting the stage right now with limits. The next time we meet, we're going to get into derivatives and get into all that, and we'll want to be pretty comfortable with the limits by the time we meet again, by the time we start talking about derivatives, because if you look ahead in 2.4, their definition for the derivative has a limit inside of it. So you definitely need limits in order to understand those derivatives, okay? So that's all that I wanted to show you today. I'll stick around in Zoom for a couple minutes. If anyone wanted to hop on there and ask me some kind of questions, you're welcome to pop into the Zoom meeting, ask me questions. I'll answer them. Otherwise, good work, everybody. Keep doing what you're doing. Keep up the good work, and we will see you in a couple days, okay?